Welcome to day 6 of calculus. We're going to do of unit 5. We're going to do something called the power rule. Now the power rule you're going to like a lot. We did this a little bit last year. It's going to be the way we're going to do derivatives from now on. So again, another name for a derivative is slope of the tangent line, f prime, dy over dx, and so on and so forth. Let's say we had a graph f of x equals a constant such as 5. That would look like this. This is f of x is equal to 5, a nice horizontal line. So what is the slope of this function? Well, the slope of this function is 0. Or, better yet, we call f prime, the derivative, is equal to 0. So whenever we have a constant, the derivative of a constant is 0, or y prime equals 0, dy over dx equals 0. Okay, that's for any constant number, whether it be -8, 2.2, or anything. So let's look at functions that we've taken the derivative of already. So we've done x squared or other things like x squared, and we saw every single time its derivative was 2x, or the dy over dx was 2x. And if I did if I did x to the third, the derivative I would get would be 3x squared. Or the dy over dx with 3x squared. Is there a pattern? Yes, there's definitely a pattern. And I hope you're going to see this pattern. It's going to be the coefficient up front times the exponent times x raised to the exponent minus 1. This is the pattern we're going to see every single time. But we have to be given a power function. That means it has to look like a times x to the n. Other examples we've done in class, we've done examples like this. F of x equals 2x squared minus 3x plus 4, and we got a derivative of f prime equals 4x minus 3. We really haven't done something like this yet because we haven't expanded an x cubed one this year, but you get the idea what's going on. Do you recognize the pattern? It is the same. It is the coefficient times the exponent and x raised to the exponent minus 1 every single time. This is what f prime is equal to. So if f prime is a constant, the derivative of a constant, because a constant is just a number, or what we call a number times x to the 0, and we do our little rule, we're going to get 0. But if it's a power function, that means it has to look like this. We're going to have to learn how we have to rewrite things to make it look like a power function, a times x to the n, then its derivative. This is exactly what I said. Coefficient times exponent, and then over here we have the original exponent minus 1. That's the pattern we're looking at every single time. It's called the power rule, or what I will call the shortcut rule. And you can use it every single time unless I tell you you have to use the actual formula that we learned in the prior days, like in day 1 and day 2 and day 3 and all that. Let's try some examples. Coefficient times exponent is 15. Lose a degree, x squared. Coefficient times exponent is 12. Lose a degree, x to the 5th. Oh, it's a fraction. Half times 4 is 2. X to the 4th becomes x to the 3rd. These are the derivatives. And what happens if we have a function with multiple terms? Well, this is just a polynomial function. We just do one term at a time. So 12x to the 5th plus 2x to the 3rd plus 15x squared. And again, the derivative of a constant is just 0. But I'm not going to write down a plus 0 because that's just a waste of time. Okay, let's try these examples on your own and make sure you write the notation. Notation is important. You will lose points for not writing the notation, such as this would be f prime of x is equal to negative 10x to the first. I'm not going to write down to the first. It's understood. Notation is important. Okay, I went through and did the rest of these examples. You can check your work. On this third one here with y equals negative 5, 6, it's x to the first. And when I really get here, it's really negative 5, 6 times x to the 0, but we never write down x to the 0. X to the 0 is just 1, so we don't even need to write down x to the 0. On this one that I did here in pink, you better be able to handle fractions. Don't ever tell me when you do negative 3 over 2 times x to the fourth, you get 12 over 2. No, 12 over 2 is just 6. Okay, you need to make sure, and 5 over 6 times 3 is 5 over 2, not 15 over 6. Yes, it is 15 over 6, but you have to reduce all fractions. Is the power rule any different when we have fractional exponents? And the answer is no. You just know how to deal with fractions. You better get used to it. You're going to have a lot of fractions the rest of this unit. Okay, so how do you subtract 1 from a fraction? Well, technically I should rewrite it as a common denominator, and I get that. A minus b over b. Or I could just look at it and say a minus b over b. But the way I really do this, I just do it as the top number minus the bottom number over the bottom number, because that's the way I see this. It is top number minus bottom number over the same bottom number, or, well, that's terrible, numerator minus denominator over that same denominator. That's the way I really subtract 1 from a fraction. So if we go through and do some examples here, again, I'm going to multiply this times this. Yes, I know it's 12 over 2, but it's really 6x. Top minus bottom is 1, and the denominator is still 2. 6 times x to the 1/2. Next example. Negative 12 times 1/3 is negative 4. Top number minus bottom number is x to the negative 2/3. And this last one is going to be, well, it's just negative 10 over 3rd. That doesn't reduce x, and it's still top number minus bottom number is negative 8 over 3. That's how I do it. It doesn't change because it's a negative number. Still top minus bottom over bottom, or numerator minus denominator over denominator. So how should I handle problems that are like this, where the x's in the denominator or have roots and radical signs? You need to know your rules of exponents. You need to know these 3 rules of exponents, that something over x to the n is a times x to the negative exponent, and something times the nth root of x is a times x to the 1 over n. And then the same thing goes when I have a power and a root, that the idea is that the numerator is the power and the denominator is the root. So when I do this problem here, I have to rewrite this as 4 times x to the negative 3, and then I have to take its derivative, and I just do the same rule I've been doing all day. Coefficient times exponent, negative 12. Subtract 1 is not negative 2, it's negative 4. You're always taking 1 away from that. Okay, I should rewrite this as 6x to the 1/2, because that's what the square root really is, and I multiply them out. I get 3x. Top minus bottom is to the negative 1/2. Oh, this is really negative 2x to the 2/3 power over root. I get negative 4/3 x top minus bottom is negative 1/3. And then finally I get, this is negative 5x to the, well, there's really a 2 here, so this is to the negative 3 over 2 power. I multiply this out, I get 15 over 2, x top minus bottom is negative 5 over 2 is my exponent. Now what happens if I have things with many terms in it? Well, I should rewrite it first. 2 x to the 3/4 minus 6 x to the 2/3. I don't have to rewrite that. Minus 9 x to the negative 1/3 plus 5 x to the 4th minus 10. And I take its derivative. So 2 times 3/4 is 6/8, or, excuse me, 2 times 3/4 is 6/4, which is 3/2 x top minus bottom is negative 1/4. And then I have negative 6 times 2/3, which is 4 x to the negative 1/3. Negative 9 times negative 3 is plus 27 x to the negative 4. 5 times 4 is plus 20 x to the 3rd, and 10 is a constant, or negative 10 is a constant. I do not, its derivative is 0. And this is what I get for g prime. Same rule as before, I'm just dealing with negative exponents and fractions. As you know, I've been making you write tangent lines, and I could rewrite it with this, where this is a number that's given to you. This is the y1 value that you find by plugging it into the original function, and this is the slope when you plug that number into the f prime. That's how I find those three things. Now when I want to do a normal line is a line perpendicular to the tangent line. So if I have a graph that looks like something like this, and that's my tangent line, my normal line will look like this. Perpendicular. And we know how to find perpendicular slopes. Those are slopes that are opposite and reciprocal. That has not changed. So let's see, let's do this problem. I have a nice function here. So f of 3 is equal to 9 when I plug it into x squared, so I have the point 39. F prime of x is equal to 2x. I could use my power rule. I don't have to go through the whole formal definition of the derivative. I plug in my number of x equals 3. I get f prime is equal to 6. So this is my slope of the tangent line. So my tangent line equation is y equals 6 x minus 3 plus 9. And my normal line is y equals negative 1/6, because that's what the perpendicular slope is. So if 6 is my slope, then my perpendicular slope is negative 1/6. Okay, like I said, if you looked at the graph of this and this was the point 39, the slope here would be 6, and the slope here would be negative 1/6. Okay, that's the idea. Let's try some examples. We have a function and a value that we can plug in. So I plug in negative 1, I get negative 1 minus 2 plus 4 plus 5. When I plug in negative 1, I get 9 minus, I get 6. So negative 1, 6 is my point. F prime of x is equal to 3x squared minus 4x minus 4. If I plug in negative 1, I get 3 plus 4 minus 4. So f prime of negative 1 is equal to 3. Now I can write my tangent line. Y equals 3, x plus 1 plus 6. And my normal line, y equals negative 1/3 x plus 1 plus 6, because that is perpendicular. Okay, so what makes this one more difficult is that I need to rewrite this function. Well, I could plug in 1 to begin with, so I could do g of 1, which is not going to be hard. I get 3 plus 8, I get 11, so I have 1 comma 11 as my point. But for me to take this derivative, I can't take it in this form. I better rewrite g of x as 3x to the negative 2 plus 8x to the 1/2. Now I can take its derivative. I get 6x to the negative 3 plus 4x to the negative 1/2. And notice I picked a really easy number to plug in for x. So g prime of 1 to any power. One to any power, doesn't matter, is always going to be 1. So when I plug 1 in here, I get 6 plus 4, I get 10. So when I write my tangent line, y equals 10, x minus 1 plus 11, and my normal line, y equals negative 1/10, x minus 1 plus 11. Okay. Once you figure out, this is why we do derivatives. It helps us find slope. Another example. Again, I have a nice easy number to plug in, so I can do h of 1 pretty easily because 1 to any power is just 1, so I get negative 5 plus 4, which is negative 1, so h of 1 is negative 1. 1, negative 1 is my point. I'm going to rewrite this function as h of x is equal to negative 5x to the negative 2/3 plus 4x cubed. So h prime of x is 10 over 3 x to the negative 5/3 plus 12x squared. I plug in 1, h prime of 1 is 10 over 3 plus 12, which is 36 over 3. Ten over 3 plus 36 over 3. H prime of 1 I get as 46 over 3. Okay, time to fix my mistakes. 3 times negative 2 is negative 6, not 6. So this is negative 6 plus 4. So this is equal to negative 2. So my slope is, these are wrong. So my slope is negative 2 for my tangent line, and for my normal line it's going to be 1/2. Those are fixed. Okay, now my other mistake. Lots of mistakes. Be nice if I wrote this correctly. This is not x to the negative 2/3. This is x to the negative 1/3. I'm going to do that in black. Negative 1/3. So this is 5/3 to the negative 4/3. And when I plug in 1, I get 5/3 plus 12, which is 5/3 plus 36 over 3. So I get 41 over 3 is my slope of the tangent line. I'm not remaking videos. This is what would happen in class if I was teaching class. And you shouldn't watch a video if you're in class or you're on Zoom anyways. I'm going to get away from that. So my tangent, y equals 41 over 3, x minus 1 minus 1, and my normal, y equals negative 3 over 41, x minus 1 minus 1. And that is the equation of my tangent or normal line. Okay, thank you for watching my video. If you couldn't watch it on Zoom, but ask questions. Thank you.